Example 4 in 11.1 deals with, it says the title, permutation with constraints, and it's really just, additional restrictions. What do we have to do when we have to deal with that? And some of them I think, are easier than the others. So if we look at part A, we have 5 people conveniently named with different letters, which is pretty typical. And it says that E has to be in the middle. Well, there's only one option for that, right? The person, Ernest, has to be in the middle. Now, for the remaining spots, there's no restrictions. So I have 4 choices, then 3 choices, then 2 choices, then 1 choice. But another way of looking at it is for these 4 remaining spots, I have 4 people and I need to pick 4 places for them to sit. Now we have the one option for the E. That's my E right there. And then this 4 pick 4 is the remaining. And the reason that it doesn't matter that E is in the middle is because we're multiplying, and the order of multiplication doesn't make a difference. And, a lot of students will still push the fundamental counting principle. That's fine. So they would put a 4 times a 3. This can be A, B, C, or D. This can be A, B, C. This is A or B, and then finally person A. And that's how, oops, that's not a 3, that's a 1. That's how the numbers kind of reflect the diminishing choices we have. There is nothing wrong with this. This will work. That means there's 24 different possibilities, but I would argue that 1 times 4 pick 4 is a little bit easier. And there are also 24 possibilities, right? Different techniques, we get the same answers. For B, I think the permutation concept becomes a little bit simpler. For part B, it says that A and B must be seated together. So the number of ways of A and B together, the number of ways that can happen is 2. And if you picture that as 2 different spots, I have 2 options, A or B, and then I have 1 option, and I'll just put maybe B remains there. So the number of ways that A and B can be together is equal to 2. I'll just put an equal sign there as well. But then what we have to do is we have to still arrange the rest of the people. There's nothing in, question B that tells me that A and B have to be the first person sitting. So what I'm going to do instead is I'm going to picture now I have the A, B conglomerate. They're together. And then I have person C, person D, and person E. And it's a weird concept that because A and B have to be seated together, it's almost as if they behave as one person. And now what I have is I have 4 different positions for them to sit. And it's really difficult to write this out, but I'm going to put for the first position, I have A, B, which is, 1 person, or C, D, or E. So what I have in that, and remember, A and B are together, so there's 4 choices there. Then I would have 3 choices, then I would have 2 choices, then I would have 1 choice. Now that is, and I'll put 4 pick 4 here. Those would be the same things. But what I have to remember is that I'm doing this, but I'm also manipulating A and B, right? I got to have A or B or B or A. So if we look at 4 times 3 times 2 times 1, which is 24, and we multiply it by 2, we actually get 48 different possibilities. And the reason why there are more possibilities in B than there are in A is because person E is locked into place in A. All right, part C is actually trickier than you might think. And the reason for that is if A and B cannot be together, I could have A first, then B could be 3rd or 4th or 5th. If A is 2nd, then B could be 4th or 5th. If A is 3rd, then B has to be on one of the ends, and so on. And you could do that with a lot of different cases. But what we're going to do instead is we're going to talk about something called the complement. And it's really tied into this chapter that if we look at the total possibilities, so total possibilities, that is going to be equal to, and what we call this is a binomial event. And I'm going to talk about an analogy here. If I flip a coin, I'm either going to get heads or tails. That's binomial, right? I either get success, it's heads, or I get failure, it's tails. We can define that. So what I'm going to do here is I'm going to make 2 situations where together they cover the entire possible situation. Now, those 2 are going to be A and B together, plus A and B apart. And I hope we agree that if we think about the total possible ways of sitting, either me and my buddy are sitting beside each other or we're not sitting beside each other. That covers every possible, scenario. And the reason why that's so important is we can treat these, because they are just numbers, and we can manipulate to solve for how many possible ways there are for A and B to be apart. And the way we do that is by subtracting this term from the other side. And I can say that the total possibilities, so every single possible way of sitting, minus the number of possibilities where A and B are together. And I spelled together wrong. That's fantastic. So the total possible minus where A and B are together is going to leave me with, so it's equal to the number of ways that A and B can be apart. Now, the reason I bring this up is because we've actually already done one of these. We just solved for part B here that there are 48 different ways for A and B to be together. So I'm just going to fill that out. I know that that is 48. And then really what we're looking for is when A and B are apart. Sometimes the complement, and this technique is usually called using the complement. The total possibility is typically not as hard as you might think. And what the total possibility really is if I have 5 people and I arrange all 5 of them, then the total ways of arranging those objects, because the order matters, is 5 pick 5. Now, if you think about fundamental counting principle, we would have 1, 2, 3, 4, 5 spots. I have 5 choices. Sorry about that. I just clicked the wrong spot there. I have 5 choices, 4 choices, 3, then 2, then 1. 5 pick 5, and 5 times 4 times 3 times 2 times 1 are the same thing. They become 100, or they are equal to 120. So 120 minus 48, which is equal to 72, is the number of ways that A and B can be apart. That is a tricky question to work with. Like I said, you could do this. I'm going to do it now because certainly I think we've come too far to not do it. We could write this out with our fundamental counting principle. I'd like to show you that I can get 72, but this is an extremely tedious way. So what I'm going to do is I'm going to draw out my 5 different people. Case 1 is going to be where person A is first. Then I'm going to draw out my 5 different options. Case 2 is going to be where A is second. Again, we have 5 different options. I'm going to put A here. Then I have 1, 2, 3, 4, 5 different options. A is here. And of course, I ran out of room. Try to tweak that a little bit. So my last case is going to be that A is in the last position. All right. Now, in order to do this, I am dealing with restrictions. So if A is first and A and B can't be together, right? That's really important. Then what I have is C, D, and E here. So I have 3 options there. Right, maybe I should have put A on the bottom, but there is only one way for A to go on into that position. All right, there was 3 options for the second position, but now my third position here, all of a sudden I can have B there because now A and B aren't together. I've used one of C, D, E, so I have D and E remaining. So I have 3 options, then 2 options, then 1 option. This would be D and E, and this would be person E. Now, if I multiply those together, 3 times 3 times 2, there are 18 ways for A and B to be apart if A is in the first position. All right, let's keep going here. We look at the next line over. This person, or to the left of A, I could have C, D, or E. Remember, it can't be B because they're apart. I have 3 options. On the right side of A, I have D or E. That's only 2 options. Another spot away from A, I have B or E. I'll put E there. That's 2 options, and then I have 1 option at the end. So 3 times 2 times 2 is equal to 12. Right, hopefully you're starting to see how tedious this technique is. Now again, I'm going to deal with the restrictions first. So beside A could be C, D, E. There's 3 options there. Then it could just be D or E. There's 2 options here. A seat away from A could be B or E. There's 2 options. And then I have 1 option remaining. I really don't like this technique, but I want to show you we get the same thing either way. And here I have 12 possibilities. All right, if A is in the 4th position, this is actually the same thing as my second case, but I want to show you all over again. The last person sitting could be C, D, or E. There's 3 options. To the left side of A, it could be D or E. There's 2 options. 1 seat away from A, it could be B or E. That's 2 options. And then this last person has to be E. I'll put that up here. Sorry, I've been overlooking that a little bit. So 2 times 2 times 3, we see we get 12 again. The last option, side A, can be C, D, or E. That's 3 possibilities. A seat away, I could have B, D, or E. That's 3 options again. This is going to be D or E. That's 2 options. And then finally, E would kind of go where he has to. 3 times 3 times 2 times 1 is going to be 18. And remember, I'm doing, one of these 5 cases. So I'm going to add those numbers together. 18 plus 18 is 36. 12 plus 12 plus 12 is 36. And what I get is 72 different ways. Now, I would like to reiterate that this is possible, but this is 5 people. What if there's 10 people? I'm going to have to make 10 different cases. That is going to be a nightmare. And I do like to at least show once or twice how to brute force a question like this, because how much easier is that complement? And we did get the exact same answer, right? There's 72 ways for A and B to be apart. or we reiterate that there's 72 different ways for A to be a part. I really want to hammer home that compliment. It is so important to understand that if you can narrow something down to, either success or failure, then success plus failure will give you the total possible outcomes, which is a pretty important consideration when we talk about probability in math.